Okay, so welcome everybody to our second day. So before starting with a scientific program, let me give a couple of announcements for on-site participants. First announcement, we have now a COVID booth for PCR or rapid test for people who need a PCR or rapid test to go back home. The booth is in front at the entrance of this building. You have to go there, get an appointment through with a QR code that you can get, and you get your data, and when you get an appointment, and you can do the test there, and we cover the expenses for one test per participant, so if you need to go back to your country. Okay, this is one thing. Another thing is if you want to change your mask, we have now some masks at the registration desk. This is the second announcement. The third thing is apparently there is some problem with internet connection with a connection with a Uni Geneva connection. So if you have EduROM, you can use that one and it should work without any problem. Okay, so if there are no questions, I think we can start with the scientific program, and Marcus Mariño is going to give his second talk on resurgence and quantum topology. So please.
Okay, is this on? Is this on? You can hear me, or? It's on, okay. Okay, thank you very much. So let's continue our discussion of yesterday. So yesterday, we started to look at this divergent series. We saw that there are two operations that you can make on them to try to make sense of them and extract information which is not apparent in the original perturbative expansion. One of them is the Borel transform, which takes us to complex analytic functions. And we saw that there is a very rich information on these singularities of this Borel transform, which gives you information which goes beyond perturbation theory. And then we saw that, again, building on this Borel transform, you can do what is called a Borel resummation, and this is essentially a kind of very beautiful operation that takes you from formal divergent power series to function, okay? But as I was trying to explain yesterday, there is a catch here because there is going to be a price to pay. So let me remind you that, okay, the Borel resummation is built on this Borel transform. It's essentially a Laplace transform. Yes? Oh, okay, so it was not on. So in this Borel resummation, you have this sort of integral, which is along a ray, and the ray is along an angle, theta, which is the argument of the variable that you want to consider, okay? Now, if you look at this integral, you see very clearly that if this Borel transform has a singularity, this integral is not well defined. But we also said that it's very important to consider, it's actually very loud, right? Yeah, okay, so. So it's very important to consider the singularities of this Borel transform, right? So what do we do when we have a singularity of the Borel transform? Well, when the angle where you are doing your Borel resummation is equal to the angle at which a singularity appears, we call the ray that goes through this singularity a Stokes ray. When our Borel resummation is along a Stokes ray, the Borel resummation is simply not well defined, okay? And then you have to do something about it. So what do we do when you have an integral and in the integrand there is a singularity? Well, in complex analysis, we are used to this type of situations, and then what you do is you deform slightly your integration contour so to avoid the singularity, okay? So we have an obstruction given by a singularity, but then we have a trick to do that. But then here we will see the actual price to pay is that when you actually deform your contour, there are many ways to do this deformation, and these different ways of doing the deformation will introduce an ambiguity in this Borel resummation. So the Borel resummation is a fantastic tool, but it has an intrinsic ambiguity due to the singularities of this Borel transform. So let me give you an example to see how this works or doesn't work. Now, remember that I showed you yesterday the simplest factorial divergent series, which is just k factorial times a to the k. And if you take this series is very, remember that we saw that the Borel transform has a singularity in the positive real axis when zeta is equal to 1. So this means that theta equal to 0, the ray that goes from the origin along the positive real axis is a Stokes ray. And then if you actually calculate the Borel resumation, you will find this formal expression when x is positive, and precisely when x is positive, there will be a singularity, and then this integral is not well defined. Now, this shouldn't discourage you very much, because this is just one direction in which this Borel resumation is not well defined. If you take other directions, you will actually be able to do this Borel resumation. For example, if you take the direction around the angle theta equal to pi, which means that you do the Borel resumation for negative values of x, this Borel resumation gives you a well-defined integral, and this integral is actually the Borel resumation of my original formal power series when the argument is negative. Okay? So you see that the Borel resumation gives you very nice results in some cases, but there are always these singularities where this Borel resumation is ill-defined. And as I was saying, you have to do this deformation, you have to use deformation techniques in order to make sense of this. And the price we will have to pay is an ambiguity that can be also interpreted as a jump in the Borel resumation. Okay? So, as I said, the way to make sense of this Borel resumation is just to deform the contours. This is the integration ray that goes around the singularity of this Borel transform. And then now you can define two different integrations which are defined by these deformations of the contour. So you have a deformation of the contour in which you go above the singularity, and you have a deformation of the contour in which you go below the singularity. So now, instead of having one Borel resumation, you have two. And this is the ambiguity, because these two integrals are going to be different. And this is precisely because they're different, in between you have a singularity. Okay? So the conclusion of this discussion is that Borel resumations are actually define you functions, but these functions are only defined through sectors. And when you go from one sector to another, the sectors are separated by these Stokes rays, and when we change your sector, this Borel resumation will jump, okay? Will jump by a discontinuous quantity. So this is the catch in these techniques of Borel resumation. They allow you to reconstruct a function out of your original perturbative series, but the catch is that your function will have discontinuities, will have jumps. So it's not really a well-defined function in the sense that it will jump discontinuously around these Stokes rays. Now, one very interesting piece of information is what is the value of this jump? What's the difference between these two lateral Borel resumations? So, in a sense, having a function which is discontinuous through rays and having the precise information about how it changes across the rays is almost as good as having a good function. So if you know exactly how this function jumps, you have a lot of control over it. And this also will have some interesting applications that I will revise in a moment. But it's a very simple calculation to calculate this continuity. So assuming, for example, that your functions are simple resurgent functions, and the details of the calculation, you can find them in the notes that are posted in my webpage. So if you want to really do this exercise, it's a very nice exercise in elementary complex analysis. So if you assume that this Borel transform has simple resurgent singularity, so log branch cuts, it's very easy to do this calculation, because essentially what you will have essentially different branches of the log on the different sides of this singularity, and then the discontinuity will essentially measure the power series that multiplies this log. Okay? And this is one beautiful application of these resurgent techniques. And then you can see that this discontinuity of one of these power series phi omega is going to be given by a linear combination of the other series that appear at the different singularities. So if your ray crosses many singularities, you will have to sum over all these singularities, and you will get a Borel resummation of all these series times the Stokes constants and times an exponential, which is just the exponential of the location of the singularity divided by x. Sorry about this misprint. This should be x, not z. Okay? So that's another very interesting aspect of these Stokes discontinuities. These are called sometimes Stokes discontinuities. The Stokes discontinuities are also another way to access all this information of this additional power series. Remember that if you start with a power series, through these techniques of resurgence, you will be able to go through this rabbit hole and get all this new information coming from this other power series by looking at the singularities. Another way of looking at these singularities is to calculate the discontinuities of this Borel resummation. They will give you exactly the same information. They will give you new power series, and they will give you also these Stokes constants. Okay? So this is essentially how the Borel resummation theory works. And then, you can think about reconstructing a theory with exact quantities, and these exact quantities are going to be Borel resummations of perturbative series, and the only thing you have to be careful is how these Borel resummations jump across these Stokes rays. So that's, in a sense, the perspective that you get from using perturbative series. You can do your favorite quantum theory, in principle, using perturbative series, but if you really want to get exact results and not just approximations, you will have to play this game. And when you play this game, your objects are going to be formal power series that you resum, and in these resummations, you will have these jumps, and then you have to be careful where you are in the complex plane in order to keep track of these jumps. And these jumps give you interesting information, and they force you to consider these other series that we found in this analysis. I will give you examples of this in a moment. Now, in this equation, you see I have formal power series, and then I have the Borel resummation. This is very important because these are mathematical objects that live in different worlds. Formal power series has formal objects, and Borel resummations give you numbers given the argument, so they are more like functions. Okay? But this is actually very convenient to encode the information in this equation as an equality relating only formal power series. And the way to do this is to introduce an operator, which is an operator acting on formal power series, which is called the Stokes automorphism. This is, in a sense, one of the most beautiful aspects of resurgence theory. So the Stokes automorphism is essentially the multiplicative difference between these two lateral Borel resummations. And if you think about the Borel resummations also as operators which go from the world of formal power series to the world of functions, you can write this equality as an equality involving this new operator, the Stokes automorphisms, and this is Stokes automorphism acting on a series phi omega at an angle theta, which is the angle where this discontinuity occurs. This Stokes automorphism is a linear combination of all the power series associated to the singularities on the ray times the Stokes constants and times an exponential which gives you the position of the singularity. Okay? And this is, in a sense, an expression which only involves formal power series. So it's a formal operation on formal power series, which has this structure here. And this is a very beautiful way of encoding this information. Again, it's also another way of encoding all the power series that are associated to a given power series phi omega. It gives you all the information about the singularities along a given ray. It gives you the formal power series associated to them, and it gives you all these Stokes constants. Okay? So in a sense, at this point of this resurgence game, we are already thinking about formal power series as sort of atomic objects, which we combine in this way by multiplying by constants and by exponentials. Now, if you look at this equation, you see that it's a new sort of type of object. It's a formal linear combination or formal power series with exponentials. And these objects here turn out to be the most general objects that you can have in a theory in which you are going to work based on perturbative series. And these series have a name, and the name that they have, it's a very beautiful name, is called trans series, okay? So, trans series are formal linear combination of power series with exponential prefactors. Okay? So, in principle, in a trans series, the only thing I have to have are formal power series, exponential factors, and then just complex coefficients psi omega, and then I can take, in principle, any sum labeled by a set omega, so this could be a finite or infinite sum. And these are the most general objects that you can have in a theory in which you start working with perturbative series. And what is very important about this is that this object goes beyond the traditional theory of asymptotic expansions. In the traditional theory of asymptotic expansions, you take a function and then you look at asymptotic expansion, and this is a formal power series in a parameter. And very often we miss information in this asymptotic expansion, and transeries are designed in such a way that you recover the full information you need to reconstruct your function completely. And we will see an example very shortly. A very important aspect of this transeries is that they include two small parameters. When you think about a formal power series, a perturbative series, you have a formal parameter which is supposed to be small. This could be the coupling constant, or this could be h bar, etc. But in a transeries, there are two small parameters. One is z, which is supposed to be the coupling constant. We are doing formal expansions around the origin. And the other is the exponential quantity e to the minus zeta omega over z. Okay? So this, when zeta omega has a real part which is positive, this is exponentially small. And this is a new small parameter. So in a sense, the message of this is that if you want to actually do exact calculations based on perturbative series, you will have to add another small parameter which is exponentially small in your coupling constant. And this, of course, for those of you who have experience with instantons in quantum mechanics or with tunneling effects in WKB method, this should ring a bell, because this is precisely the type of information that is typically not accessible to perturbative expansions, but is recovered through these exponentially small terms that appear in a transeries. Okay? So transeries are, in a sense, the upgrade of perturbative series in such a way that we will be able to obtain at the nth exact result. And the idea then is you should be able to reconstruct these exact results by taking transeries and doing Borel resummations of it. Okay? Now let me give you an example, because this has been quite abstract, I assume. Let me give you an example. Let's go back to our example of the 80 functions. Remember that when we were looking for nice examples of formal power series, we ended up with these two formal power series that appear in the study of the asymptotics of 80 functions. So one is phi1 of z, and the other is phi2 of z. Okay? So phi1 of z is this formal power series that we study here. It's a simple Resurgence function. We'll have its Borel transform will have log singularities. Remember that the study of the single singularity of the Borel transform of this series gives you this other series, so they are related by this relationship of this Resurgence relationship. But now we want to see what you can do if you do Borel resummation of this series. Now, if you look at a kind of traditional book on asymptotics of functions, the book will tell you that the 80 function has an asymptotic expansion for large argument, which is essentially given by this series here. But it turns out that this classical asymptotic statement can be made into an exact statement by using Borel resummation. So there is this exact result, which says that if you take this formal power series and you take the Borel resummation of it, you will actually reproduce the 80 function. Here you have to be careful, because the argument z appearing here is related to the argument of the 80 function by this relationship. And this equality is only valid in an angular sector, which is specified here. It's the angular sector in which the argument of x is smaller in absolute value than 2 pi over 3. And this is what you should expect, because I told you that Borel resummations jump around rays. So any statement about Borel resummations is only going to be valid in principle in an angular wedge. But you see, this is an important upgrading of the standard asymptotic analysis. In asymptotic analysis, you just know that this formal power series gives you a good approximation to the 80 function. But this is not an approximation. This is an exact statement. This is with an equality sign here. So when you do the Borel resummation of this series, you will get an actual equal sign for the 80 function. Okay? Now, what happens? Remember that this power series phi1 has a singularity. And along this singularity, there will be one of these Stokes rays. Remember that all singularities of the Borel transform will give you discontinuities in the Borel resummation. So what happens when you start moving the argument of this function, or equivalent, you start moving the argument of this Borel resummation, and you hit the Stokes ray? Well, when you go through a Stokes ray, there is something dramatic that happens in the Borel resummation, which is a jump. So you cannot expect this expression to be valid anymore. And actually what happens is that after you cross this Stokes ray, the 80 function is still given by a combination of Borel resummation, but it's a different one. And this combination is phi1 times a small exponential, times an exponential, plus the Borel summation of phi2 times another exponential. Okay? So you can actually see, if you remember that x to the 3 halves is 1 over z, you can see that this object here is precisely of this form. It's a combination of formal power series plus exponentials. So what you can say is that the 80 function here, it's a Borel resummation of a trans-series, of a linear combination of formal power series with small exponentials. Okay? So that's why we say in the theory of resurgence that if you are lucky, you can reconstruct an exact function from this Borel resummation of not a single formal power series, but a linear combination of formal power series with exponential factors. And you can see that actually, if you want, this term here is going to be an exponentially small corrections to the first term here in some regions, or vice versa. But the two terms that are here are going to have different exponential weights, and you can think about them as exponentially small corrections to the other. And this is very important because exponentially small corrections are just invisible in classical asymptotic analysis, just purely invisible. Okay? Okay, so of course, you know, in the world of special functions, it's very easy to do this game, and you can actually reconstruct many functions by doing this Borel resummation. And actually, it's very interesting that in the last version of the digital repository of special functions that you can find in the internet, now the asymptotic expansions of the special functions are actually written as trans-series. Okay? So this kind of trans-series knowledge that comes from the theory of resurgence is now slowly incorporated into the database for special functions. So you look, for example, at the asymptotics of Bessel functions or other special functions, you can actually very typically upgrade the classical asymptotic expansions of all these special functions to exact Borel resummations by using the appropriate trans-series. Okay? And this is extremely useful, even in practical applications, of course. So what is this? What is the resurgence program? Well, when you find all these results, you can have this wild dream that, in a sense, you can try to reconstruct any quantum theory by just using perturbative series plus this trans-series and Borel resounding and reconstruct everything you want. Okay? So instead of trying to make sense of the path integral, which is very hard, you forget about the path integral, you calculate all these perturbative series, and you try to see if by Borel resumming the appropriate combinations of them in this trans-series, you can reconstruct your whole quantum theory. That would be a fantastic dream, and that would be a very, in a sense, it's actually an approach which is very down to earth, because as I said yesterday, most of the quantum field theories doing calculations at LHC are doing actually perturbation theory, right? In QCD, this is still a very important approach to do calculations and in the standard model. So this approach would be actually very close to what many people actually do in order to understand physical theories and apply them to the world. Now, is this program, I mean, this is a wild program, this is a wild dream, I mean, semi-wild, let's say. I mean, it's not completely wild because there are some cases in which this program is successful. And actually, this program has been extremely successful in a simplest quantum field theory we know, which is quantum field theory in one dimension, also known as quantum mechanics. In quantum mechanics, this program works very well. And it's actually relatively old results that in many cases in non-relativistic quantum mechanics, the energy levels, for example, the spectrum of many potentials, in particular polynomial potentials, can be always written in terms of a Borel resum trans-series, so in terms of linear combinations of these formal series with exponentially small terms, exponentially small corrections. So you can write the energy levels in terms of Borel resum trans-series in an appropriate coupling constant. So the appropriate coupling constants could vary. It could be the coupling of the potential, so the strength of the potential, could be h bar, but you can actually do that. And this actually gives you, for example, exact quantization conditions for potentials which are not exactly solvable in the classical sense. Remember that in the classical sense, there are very few solvable potentials in quantum mechanics. You have the harmonic oscillator and then other sort of exotic potentials. But by using this theory of resurgence, you can write exact quantization conditions, for example, for any polynomial potential. In the sense that you can reconstruct your energy levels by using Borel-resumed trans series. Okay? Now, of course, quantum mechanics, we know it's very simple. You cannot pass your life doing quantum mechanics because this is a very special world. So the question would be if you can actually do this in an actual quantum field theory or in a quantum many-body system, in a non-relativistic quantum field theory, where this is a kind of more complicated thing. But you see, when you want to do this, you have to be careful. You have to try to be realistic in many senses. You have to try to be realistic in the sense of looking at a quantum field theory, which is more or less interesting, but you cannot jump onto QCD directly because Jan-Mills theory or QCD are complicated theories. So you want to test a program, you better test it little by little, right? So one thing you can try to do is to think about a theory, a quantum field theory, which is sufficiently complicated, but has some simplifying feature. And we have many quantum field theories which have simplifying features that can be, for example, integrable, that can be, for example, supersymmetric, or they can be topological. There are special types of quantum field theories in which, for which this program of resurgence might be more amenable to success. And in a sense, what I'm going to discuss in the second part of my lectures, which is going to start now, is a particular quantum field theory, which is of the topological type. It's called Chern-Simons-Gauge theory. And in this theory, you can actually make this program of resurgence extremely successful. And we will see that this theory leads to very rich perturbative series and trans series that can be described in detail. And for this series, you can actually describe, for example, in whole detail, the structure of singularities in the Borel plane, of the Borel transform, and so on. Okay? Now, I will talk about Chern-Simons-Gauge theory in a sort of progressive way, but you can think about Chern-Simons-Gauge theory as some sort of simplified version of Jan-Mills theory in 3 dimensions. Jan-Mills theory in 3 dimensions is the theory that Martin Heidegger is discussing in his lectures. Jan-Mills theory is a complicated theory, but Chern-Simons theory is like a simpler version of a gauge theory, and it's a version for which you can actually try to make progress with this program. Okay? So now I'm going to kind of switch gears and apply everything that we have learned to this particular gauge theory, which is Chern-Simons-Gauge theory, but I will introduce it in a geometric way. I mean, we will come back later to the actual theory a little bit, but I will try to introduce it in a more geometric way. So this is maybe a moment for questions. Do you have questions about what we have done so far? Okay, so what is this Chern-Simons-Gauge theory? Well, the way I will talk about this is by talking about knots and knot invariance in 3 dimensions. And this is because these two things are essentially equivalent, but it's much easier to do a geometric approach to this theory by focusing on invariance of knots. So I will actually, what I will do is I will to present you a very well-known classical invariant of knots, which is the Jones polynomial, and then we will see how to extract like divergent series from this Jones polynomial, and this will be our route into Chern-Simons theory. We're not going to use the Lagrangian and all this because this is relatively complicated, so we'll use a more geometric thing. Now, one of the pieces of genius of the Jones polynomial is that it's an extremely easy object to define. So the Jones polynomial is not complicated, and then, you know, it's a relatively easy object. So a knot, it's something like this. It's an embedding of a circle into R3, and mathematicians have worried for a long time about how to define algebraic invariants of these links. Now, 2 links are equivalent. You can deform one into the other without breaking the rope, if 2 knots are equivalent, their algebraic invariance will be equivalent. So people found that it's very interesting to define invariance, algebraic invariance of these knots, which are polynomial in some variables. And this is what Jones did in his groundbreaking work in 1985. So I draw here a knot, which is one of my favorite knots. It's called the figure 8 knot. It's a knot which, when we draw it on a plane, has 4 crossings. Okay? So you see that these are the crossings of a knot. These are the places where you, since the knot has a non-trivial topology, you are forced to cross them when you project it in a plane. So this knot has 4 crossings, 1, 2, 3, 4. So this is the only knot with 4 crossings. And it's one of the knots that I will use as an example in many of the things I will do. I like to present things with examples, so sometimes I won't be general, but I will refer to this figure 8 knot as kind of my favorite knot example. So knots are actually oriented. This knot here, I didn't write an orientation because I took this picture from the Wikipedia, but an orientation is just simply a direction of traveling around the knot. So when you write an oriented knot, you have to put an arrow which can go into this direction, so you would travel in this way, or you can use the inverse orientation. Okay? And then Jones defined an invariant of a knot and links. A link is just a collection of knots, in which instead of having one circle which is twisted, you have many circles. Okay, so this is one, I'm going to call that a link. Now, the Jones polynomial is an invariant of an oriented link. So a link in which all components, which are knots, have been assigned an orientation. And it's an algebraic object, it's a Lorentz polynomial in a formal variable q to the 1/2. And there is actually a very easy way to define it. I'm going to present it here. If you want more details, you can actually spend your whole life doing calculations of this type. And I spent a lot of hours when I was a graduate student, doing this type of calculations. It's a very good exercise. So you can actually define the Jones polynomial by a formal procedure which is called a skein relation. So it's a recursive procedure. So how does it work? Now imagine that you look at a knot, an oriented knot, and you look at one of the crossings. And imagine that the crossing is of this type. Okay? So this is called, I will call this type of crossing L+. Now, you can generate 2 different knots or links from this crossing by doing 2 different operations. One is the inversion of the crossing, and the other is the undoing of the crossing. So when you have a crossing like this, you can change it by changing the orientation of this, the superposition of the strands, or by undoing this, or by undoing the crossing itself. If you do this operation of the crossing of the knot, you will find 2 other knots, which differ from the original one by these operations. And then what Jones found is that the Jones polynomial of the original knot is related to the Jones polynomial of the knot oriented in this way and in this way by this simple algebraic relation. Okay? And it's actually possible to prove that if you use this recursion, I give you a knot and you use this recursion repeatedly, you will be able to compute the Jones polynomial of the original knot recursively. It's a recursive procedure. And in order to actually finish the calculation, you have to tell me what is the value of the Jones polynomial in the simplest knot, which is the trivial knot, in which there are no crosses that can be undone. And this is called the unknot, and a usual normalization is to take j of q equal to 1. And by doing this, you can have fun for one afternoon. For example, calculating the Jones polynomial of this knot here, and it's given by this formula here. It turns out that at the end of the day, that the Jones polynomial of a knot, that doesn't depend on the orientation you choose. So if you choose an orientation or the opposite one, you will get the same object for knots. So this is, for example, the Jones polynomial of the figure of this knot, which is called the figure 8 knot. And you can see it's a Laurent polynomial in q to the 1/2, in this case, given by this expression. Okay? Very good. Now, the Jones polynomial has been tabulated. You can have, you look at the knots, at the encyclopedia of knots, you can have the Jones polynomial of all knots up to 10 crossings. So it has become a very powerful invariant and a very powerful, interesting object in itself. So why do we actually want to look at this if we are interested in quantum field theory? This is because Edward Witten, who is shown in this picture, show that actually this polynomial of knots can be obtained by doing a calculation in a quantum field theory. It's an observable, so is the vacuum expectation value of an operator in a theory called Chern-Simons theory. And I will later give you a little bit more details, but this theory is actually an interacting gauge theory. It's a theory in which you have a non-trivial interaction. You can actually do perturbative expansions in this theory, and in this theory you have a coupling constant, which is something like similar to h bar, which I'm going to call tau here. And in this theory, it's a little bit special because tau has to be of the form 1 over an integer number. Okay? That's a particular property of this theory, but you see, this is actually not that important when you do perturbative calculations because the only thing that you want is that your coupling is small. And of course, if k is a very large integer, this tau is going to be small, so you can do perturbation theory. Now, we then found that this variable q that appears in the Jones polynomial, which is in a sense like a dummy variable, a variable which has no meaning, is actually related to this coupling constant. And it's simply equal to the exponential of 2 pi I times this coupling constant. So in a sense, if you think about the Jones polynomial from this Witten's perspective, it has a coupling constant behind, and then once you have a coupling constant, you can think about doing perturbative expansions. You think about how these objects that you compute actually organize into perturbative series. So why we would like to do this? And this is a moment to actually question why, if you have an exact answer, the Jones polynomial is a function of q, and then, what is interesting at all to think about q as the exponential of some small parameter and expanding in powers of this parameter? Well, the reason is actually very deep, and is that very often in quantum mechanics, you do a calculation, which is maybe an exact calculation, but this doesn't give you a feeling, a kind of an interpretation of this object. And this is something in the sense that already in quantum mechanics, in the sense of what is the classical limit of quantum mechanics. When you take a quantum mechanical object, we are supposed to get a classical feeling of this object by going to the limit, for example, in which h bar is small. And in the semi-classical limit of quantum mechanics, you see many aspects of quantum mechanics which are related, for example, to classical intuition. Now, the Jones polynomial is a very quantum object. It's an object which is defined by an algorithm which doesn't really give you much information about the knot. I mean, you have to do these skein relations and so on, but at the end of the day, what is really the information about the geometry of the knot which is encoded in this combinatorial game, right? This is something which is not easy to understand. Now, one could hope that by doing this kind of semi-classical approach, some more geometric aspects of the Jones polynomial will appear in the game. And this is the reason why we are doing this. We shouldn't lose this kind of goal, because that's actually the main reason why we want to do these perturbative expansions in quantum topology, to try to see if these quantum invariants that were defined in a sense very algorithmically or very abstractly have some more visible information about the knot. And we will actually see that this is the case, and we'll actually find some very interesting surprises. Now, let's then try to do this. Now I just defined my goal, let's try to do this. But then, remember that in resurgence theory, we want to do expansions which are divergent, which are really the typical expansions in quantum theory, which are divergent. But you see, you are never going to get a divergent power series from the Jones polynomial. Jones polynomial is a polynomial in Q, use the exponential of tau, so you're only going to get, it's an entire function of tau, so you're only going to get convergent series, and actually series with an infinite radius of convergence. So it looks like there is no room for doing this type of game with the Jones polynomial, right? Well, you don't have to be discouraged, because actually people found that the Jones polynomial has hidden inside it at least one divergent power series. And I'm going to try to kind of give you a flavor of how this goes. Now, in order to do that, there are many ways to approach this problem, but one way to do this is to consider a variant of the Jones polynomial, which is called the color Jones polynomial. Now, the Jones polynomial is this object that I defined. Now, I will introduce a generalization of it, which is called the color Jones polynomial, which is labeled by an integer n, which is a positive integer. Okay? So I'm going to define a family of invariants Jn of Q. Well, I'm not going to define it totally. I'm going to give you a flavor of how it goes. And there are many ways to doing this, but essentially, I'm not going to give you the details because this gets a little bit complicated and it's actually not completely central, but it's actually something that can be done also algorithmically. Essentially, what you have to do is when you have the knot, you have a knot and you want to compute this color Jones polynomial, you have to replace the rope of the knot by n-1 copies of it, and then you have to twist these ropes appropriately, and then you will get a complicated link, and then this link, you can compute this Jones polynomial, and this is the color Jones polynomial, okay? Now, believe me that this is what you should do. And of course, if n is equal to 1, you get 0 copies of your own knot, so you don't get anything, and you normalize this to 1. And when you have n equal to 2, you just don't do anything, because you just don't have to replace the row by, you just replace the row by itself, and you obtain the original Jones polynomial. So the color Jones polynomial is a family of polynomials, which is labeled by this positive integer, such that for n equal 2, you recover the original polynomial. And this, again, you can play with it. You can spend your afternoons computing this Jones polynomial. And for example, for the figure A knot, you can get a very explicit expression for what this color Jones polynomial is, and you get this expression here, and it's very funny to check that when n is equal to 1, this is 1, and when n is equal to 2, this is the expression that I showed you before. You can do this as an exercise, okay? So this is the color Jones polynomial. It's just a slight generalization of it. Now, what is very surprising is the following. For any positive integer n, this is, again, a polynomial, so its perturbative expansion will give you just a convergent power series. But let's imagine that you want to write this expression, you want to write this expansion for an arbitrary value of n. So what you do is, you actually expand this in powers of tau. You do this expansion in which q is e to the tau, essentially, you expand in tau, but then the coefficients will depend on n, and imagine that you just want to do this for different values of n, then this is actually what Melvin and Morton did, two topologists, and what they found is that actually these coefficients, as functions of n, they are polynomials in n of a fixed degree, okay? So when n is a positive integer, this series is convergent. But what they found is that if n is not a positive integer, this series is factorially divergent. It's quite a special situation that arises here. And the simplest case is n equals 0. When this n equals 0 is not part of the definition of the original color Jones, but once you do this perturbative expansion, you can do it. And when you do this, you obtain a factorially divergent series, which I'm going to call phi 0 of tau. So the message of this is that given any knot, I'm going to be able to associate to it a factorially divergent power series, which is Gebre 1. Okay? And this is a power series that encodes information of this Jones polynomial in some way, and encodes information about this color version of the Jones polynomial. But you see, until now, we haven't seen a lot of geometry here. It's just this is just a game, but at least we have take this game into the arena in which we can use resurgence theory, and we can use the analysis of perturbative series that I have been trying to explain. So, let me give you an example to see that this is something very concrete. For the figure A knot, you can actually calculate this phi 0 very quickly, and you can actually calculate it from the expressions I showed you, and you find a divergent series, a factorial divergent series, which only involves even powers of tau. This is just an accident because of this knot has a very peculiar symmetry properties. In general, you just have a formal power series of tau. And then now, presented with this, you can think, okay, what is the resurgent structure of this object? I mean, I have a power series, I can do a Borel transform. So what kind of information about, for example, the singularities of the Borel transform of this knot can I obtain? And does it have some interesting geometric information on the knot? Okay. So essentially, now I'm just telling, if you want the message that I'm telling you is that perturbative series are everywhere, and even in the study of topological invariants, you can end up with interesting power series. Very good. Now, I'm going to give you the result of the resurgent structure for this figure A knot, and this is actually a very, it's nice that with what I explained you can already understand this plot, but this is a result actually that we obtained this summer, that we obtained a few weeks ago, with Stavros Garoufalidis and Diego, who is here, and Campbell Wheeler. Now, what we found, and this is just an example, what we found is that the Borel transform of this power series, which is a power series which has been known for many years. This power series has been known for many years. The Borel transform has two infinite towers of singularities on the complex plane. Now, the singularities are are separated by 2 pi I in the complex plane, and then the real part of these singularities are V over 2 pi. And what is V? V is the hyperbolic volume of the complement of the knot. So what is this? Well, the knot, this figure A knot, is a kind of generic type of knot. It's called a hyperbolic knot. A hyperbolic knot is a knot such that its complement, it's a Riemannian manifold, admits a complex Riemannian metric of constant negative curvature, and in this constant negative curvature, you can compute its volume. So the figure A knot is the simplest hyperbolic knot, and this is the first surprise. This series has encoded in it through these singularities a totally classical geometric property of the knot, which is completely invisible in the original Jones polynomial, which is the volume of the knot. And this is not just an accident of this knot, it's a generic property of hyperbolic knots. So by looking at this perturbative series and doing a semi-classical analysis in that sense, we have found a classical property of the knot, which is not as manifest in the Jones polynomial, which is the volume of the knot. So metric properties of the knot are encoded in this resurgence structure. So I will stop here because my time is over, and we will resume this tomorrow. Thank you.
Thank you very much. Are there questions? Yes, please go ahead. Maybe you need a microphone. It's coming.
I'm just curious why this is the conjecture. It's impossible to calculate the singularities, or?
That's the thing, you know, we have calculated some of these singularities numerically, but to prove that this series has exactly this pattern of singularities is still open, I think. We have concrete evidence that this is the structure of singularities, and we have a kind of complicated theory where this fits very well, but this is still not proof. In order to prove this, you will have to actually take the Borel transform and analyze its singularities strictly, you know, and found all the list of singularities, and this we haven't done. One reason why this is not so easy is that this series, it's not known in closed form. You don't have a closed form for its coefficients, so we don't really have an analytic form for the Borel transform. So this is an interesting open question. We haven't, I mean, as I said, this is a very recent result, so maybe with a little bit more work we can prove it, but right now we just have a conjecture about this. But we have a lot of information about this, not just this thing here. So there is a whole theory where this fits very well, so we are actually pretty sure that this is the structure.
Thank you.
But it's an interesting open problem for people in the audience.
Are there more questions? There is one over there. Should I bring the mic? Sorry.
Do you need to renormalize the volume somehow? So why is it not infinite or dependent on the space you embed the knot in?
Yeah, this is the complement of the knot. Sorry, you are right. This is the complement of the knot on S3. Okay? So it's S3 minus the knot. Usually as you say, you compactify usually the knot. The knot is usually embedded in R3, but you compactify by just a one-point compactification to S3, and this is the volume on S3 minus K, which is this is the space where you can define this complete Riemannian metric. Yeah. So you have to go to S3.
Okay, there is another question here, I see. Sorry. Maybe this is closer and then we can get to over.
Thank you. So do you expect, if the volume tends to 0, then you expect that the series has no singularity? I think the unknotted is a torus, so maybe I'm saying a stupid thing, but the torus is Euclidean, and then the volume, what is the volume in this case? My question is, if there are Euclidean knots in the same sense, and if in that case the function will have no singularities.
I don't fully understand the question. So what's the question about? What's
Okay, there are cases in which this volume goes to 0.
Yes, for torus knots, this volume is 0. Yes, absolutely.
And in this case, the function has no...
In these cases, actually, I have to say that this case is in a sense simpler. For example, take the trefoil knot, which is the simpler torus knot. This is a case for which the volume is 0. Then the structure of singularities is slightly different. And this has been understood completely analytically. There is an old resource of Stavros Garoufalidis on this. But this is, in a sense, a different class. Here I'm focusing on hyperbolic knots, so this is a hyperbolic knot. But for trefoil knots, you can do the same Resurgence analysis, and you will find other location of the singularities, which is not, of course, related to the volume, because the volume is 0. So there is for torus knots, the story is slightly different, and there will be singularities, but are not, of course, directly related to the volume of the knot, because it's 0, as you pointed out.
Okay, thank you.
But there is a paper where that's been completely worked out, and the beautiful thing about torus knots is that, in a sense, they are much simpler, because you can write this series has a closed form, and then you can write down the Borel transform completely analytically, and you can find the location of the singularities analytically. So it's, in a sense, it's a nicer case.
I think there was a last question, maybe.
Thanks. So I assume you found like exponential corrections to in the trend series, right? Like, so my question is, do they still have an interpretation in terms of instantons? Or?
Absolutely. This is actually what I'm going to do in my last lecture. In my last lecture, I will try to give an heuristic explanation of why this is the case. Okay. And we will see that this involves a very non-trivial thing, which is the complexification. In order to really account for this, you will have to complexify your theory. And this is something that people understood in quantum mechanics long ago. And this is a non-trivial example in quantum field theory where these complexifying instantons play a very important role. So these singularities, I just can tell you already now because you're asking this question. These singularities will correspond to complex instantons of the theory.
Okay. Thanks.
Okay, if there are no more urgent questions, since we are, is it a short question or, okay, maybe there is a last short question over there in the middle. Can you bring it? Thank you.
Yes. No, very shortly, I was wondering if there was any connection between the core Jones polynomial and the replicate trick.
The what?
The replicate trick, where you take many copies of a single system and glue them together.
Can you
the replicate
speak louder, please?
The replicate trick.
The replicate trick?
Yes.
Oh. Well, I wouldn't say no directly. No directly, because in the replica trick, essentially you take an operator and you take the operator to the power of n, and then you take the trace. But I would have to think. Maybe there is some sort of maybe there is a way to calculate the Colorion polynomial in which you can write it in this way, of trace of rho to the n. But I'm not completely sure about it. There are other invariants which have an structure which is related to the replica trick, but I'm not sure that for the Jones polynomial this is actually the case. I think you probably have to do some sort of symmetrization or an additional tensorial operation in order to get the Jones polynomial in this way.
Okay, since we have to run to the next speaker, so let's thank Marcos once again. Thank you very much.